Namaskar my dear friends. Let's start with intelligent power module design techniques. So we are going to discuss about Mitsubishi Electric SLIMDIP packages. So SLIMDIP IPM is one of the most popular IPMs that is there in right now in market. And as you know, Mitsubishi Electric is the pioneer of IPM. Mr. Majumdar is the the god of this particular IPM design and putting in a particular package. Okay. So once we come to know about this particular intelligent power module from Mitsubishi Electric, our design and discussion will be very complete, and any kinds of applications, whether it is a motor drives for home appliances or automotives or some other industrial motor drives, all of them can be taken into account with the help of Mitsubishi Electric as well. Okay. So we will be concentrating on SLIMDIP-S. So what about SLIMDIP-S is basically, you know that it has VCES of 600 volt and the current rating of 5 ampere. So basically we are going to see the lowest end of IPM available with Mitsubishi Electric, that is SLIMDIP-S series. The same SLIMDIP-S has other parts which is having dash M, dash L, dash W and dash X. So X will be the highest current rating and S will be the lowest current rating. Okay. So as you can see, the collector current rating for S to X is varying from 5 ampere to 30 amperes, and the collector to emitter voltage rating is going to be 600 volt. Some of the most like features that is there with this particular SLIMDIP IPM is SLIMDIP-S IPM is basically, you can see for P side, drive circuit, high voltage, high speed level shifting and control supply under voltage protection is also there. For N side, same way we have under voltage protection as well as short circuit protection, and we have over temperature protection also. So P side we have under voltage protection, N side we have under voltage protection as well as temperature protection and short circuit protection. We have fault signaling also. So if there is any fault in the N side IGBT, then there will be a fault signal that will be generated, which can be monitored through the microcontroller. Okay. We have temperature monitoring. As you can see that outputting LVIC technology by analog signal, we have what is the temperature of this particular IPM while working, that can be taken into account. And it has a compatibility of 3 volt and 5 volt schematic triggers. So if you want, you can utilize both the logics, let's say 3.3 volt as well as 5 volt for your control signals. And it is having other packages like DIP IPM, Slim DIP IPM, DIP IPM Plus, then SOP IPM, we have DIP PFC, and as well as we have CST BT. So these are the trademarks that's of Mitsubishi Electric Corporation. So first of all, our main intention is to understand what is SLIMDIP-S series and what are the different applications that it can be utilized for. So there are various applications that it can be utilized for. The very first one is air conditioner. So you can see we have ODU unit, that is outdoor units or something like that, in air conditioners, so that can be utilized. We have cloth washers, that is basically nothing but like washing machines. We have refrigerators, we have dishwashers, we have fan, we have pumps. So fan like a lower power industrial fan also, and like water pumps and all can be using this particular SLIMDIP-S IPM. Okay. If you see some of the features about this particular IPM, you can see just now I told you the voltage between collector to emitter is like capable of 600 volt. The current rating is 5 amperes, and it can take isolation voltage of 2000 volts. That's the important thing, right? So the isolation voltage of this particular IPM is 2000 volt. The junction temperature that it can work up to 150 degrees centigrade. And if you talk about connections, so it has 3-phase inverter with driver ICs. Okay. Coming back to the package type, so we have a slim package. This is actually a trademark of Mitsubishi, so that's the reason it is called as slim dip. Okay. And coming back to the supply situation, so basically it is in production, so nothing to worry about, and it is also UL recognized with the UL 1557. So as we have understood the importance of this particular IPM that we are going to discuss about from Mitsubishi Electric, so let's open the data sheet and try to understand different parameters or different features and understanding about this particular IPM. So what we'll do is, as you can see, we have Mitsubishi Electric IPM here. So as we can see, this is the outline of this particular SLIMDIP IPM. We have actually these are the pins that is available. Okay, so we'll see pin one by one. And just now we already talked about the features and what are the P side and N side functionalities and fault signaling and temperature monitoring. If you talk about main functions and ratings of this particular IPM is, it has RC IGBT inverter bridge for 3-phase AC to DC power conversion. We have built-in bootstrap diode. So bootstrap diode are built in with current limiting resistors as well, and we have open emitter type. If you talk about application, just now I told you like it can be used in lot of motor driver applications. Okay. Moving to the internal circuit diagram, so if you see internal circuit diagram, we have pin number like 1 to let's say 20 pin and 21 to total 27 pins. So this is a 27 pin device, and these are the low power like low voltage supplies. So VUFS and UFB. So basically U phase, V phase and W phase. So this is the low voltage supply that will be taking up 15-volt inputs. Okay, and we have UP, VP, WP, that is nothing but the signal that is coming from microcontroller. Okay, so that will be my PWM signals. Okay, similar to that we have UN, VN and WN, that will be the other three low side switching like logic supply. This is high side logic supply, that is UP, VP, WP, and this is low side logic supply, which is UN, VN and WN. Okay, some other pins are there, like let's say this is my fault output and this is my scene, that is nothing but comparator input for the output current monitoring that will be there through the sense resistors. So we'll see that one in our circuit design. And we have over voltage temperature protection here. So whatever the temperature that is there of the IC while working, that can be always monitored through the ADCs. Okay, coming back to the output side, if we have like a U, V and W phase that can be connected to the 3 phase of our motor, and we have, this is my positive supply which will be taking the high voltage supply of up to around 400 volt or 500 volt. Okay, so basically we try to give 300 to 400 volts DC rectified DC signal with a DC link capacitor or something like that. Coming back to this one, NU, NV and NW, so these are the 3 pins which will be used to connect to the lower side of the high voltage DC, which will be actually connected to the sense resistor, and that sense resistor will be monitoring the current flowing through the IGBTs. So either we can utilize 3 sense resistors separately in each one of them, or to reduce the cost of design we can utilize single resistor to the single resistor for current monitoring. Coming back to the next part, if we talk about we have maximum rating capabilities. So if you see maximum ratings, so for inverter part we have VCC, which is going to take up to 450 volt, which will be applied between P and NU, NV, NW. That's the reason I told you positive supply and something like that. If we have some surge voltage, then surge voltage will be taking 500 volt, and what is the collector emitter voltage? So that will be 600 volt. If you talk about each IGBT current collector current capacity, that is 5 ampere, and if there is a peak current that is coming to IGBT collector current, that can take up to 10 ampere for less than 1 millisecond. Okay, so if there are some pulse of higher current rating which is coming for less than 1 millisecond, it can withstand up to 10 amperes. If we talk about the junction temperature, it can work up to as high as 150 degrees centigrade. So these are the parts that were there for inverter part of this particular maximum rating for this SLIMDIP. Okay, now let's talk about controller part. So if you talk about controller part, my control voltage supply, that's what I was talking to you, which is low voltage supply, which will be VP to NC and VN to NC, that will be maximum 20 volts. Similar to that, we have control supply VDB, so that's the reason I told you VUFB to UFS, UFB to VFB to VFS and WFB to WFS. So U, V and W phase, thus these three phases it can take up to 20 volt. Coming back to the input voltage, so input voltage between UP, VP, WP and UN, VN, WN, that is nothing but a logic supply which is going to come from the microcontroller PWM signals. That can also be isolated, non-isolated, can be buffered, so and with some filtering circuits. All those circuit design techniques we will try to understand. However, this particular input voltage can take up to VD plus 5 volts. So VD is your control supply which is going to be 20 volts, so it will be 20 plus 5, but these are the maximum rating. This is not recommended rating. Okay, recommended rating will be lesser than this. Okay, coming back to fault output supply voltage, so that is going to give us fault output supply which will be VD plus 5 volt maximum, and fault output current can go up to 1 milliampere. Okay, we have current sensing input voltage that is going to take up to VD plus 0.5. So VD is nothing but the low voltage supply that will be there for the controller part. Talking about total system, so total system, if you see, we have VCC which is going to be self protection supply voltage limit, that is short circuit protection capability, so that can take up to 400 volt. Okay, and generally the condition is tested for VD is nominally 15 volts. So that's the reason in all IPMs generally whatever I have designed for various applications, we have always used VD as 15 volt for the controller part. Coming back to the module case operation temperature, so that is going to be minus 30 to 115 degree centigrade, and isolation voltage, as we already talked about, it is 2000 volt, that is 2 kV. So this is the IC that is there. You can see the figure of this particular IC, and it has a very good capability of putting the heat sink properly, and this is the chip position. Okay, and these are the controller terminals, so these are little bit closer together. These are the voltage supply for control part, and this is the output side which is having motor control like motor connectors and the current sense resistor as well as DC supply. So you can see we have heat sink connection very properly. Coming back to thermal resistance, so it has a very good thermal resistance which is of 5.4 Kelvin per watt. So for 1 watt of power dissipation across the IC, there will be an increment of 5.4 Kelvin. Good. So moving on to the next part, coming back to the electrical characteristics. So if you see electrical characteristics, we have voltage across collector to emitter in saturation mode. So basically collector emitter saturation voltage will be close to 2 volt, you can say, like 1.85 to 2.25 volt maximum. So these are there for almost all the ICs that we have already studied. Coming back to forward voltage drop of this particular VCE, so that is also 1.5 volt. Okay, so it is nothing but FWDI is nothing but the forward voltage drop across the diode, right? Emitter to collector diode. And on time, off time, all these things, if you want, you can have a look on this particular values which is in microseconds. Coming back to the control part, so control part, if we see, the ID current is around 3.1 milliamperes. So if you see circuit current that will be taking through the logics, then it will be around 3 milliamperes. So if you talk about P side control supply which is UVDB and UVDBR, so that is going to be 10 volt, right? That is your trip level and reset levels. So what do you understand about this P side control supply under voltage lockout? It means it will not start before 10 volt. So that's the understanding of under voltage lockout protection. So below 10 volt the circuit will not work out. Talking about over temperature protection, so over temperature protection, you can see it has 130 degree centigrade and hysteresis of 10 degree centigrade. So suppose let's say it has tripped at 130 degree centigrade, it will bounce back again after it reaches to 120 degree centigrade, then only it will come back to normal operation. And we have fault output voltage that will be minimum 4.9 volt. Okay, and the lower voltage will be 0.95 volt maximum. Okay, so lower logic, higher logic will be there at the fault output voltage. So as you can see, fault output voltage, higher logic will be minimum 4.9 volt and lower logic voltage will be maximum 0.9 volt. So that's the understanding we should have. Good. There are other parts that we'll just talk about. Let's say bootstrap diode forward voltage. So bootstrap diode forward voltage is 1.7 volt, and we have built-in limiting resistance which is included into the bootstrap diode, that is 100 ohm. Moving to the next part, which is going to be some characteristics. So as you can see, based on the forward voltage supply, let's say up to 15 volt, we have a forward current as well. So it is reaching up to 140 milliampere. So that's the characteristics of bootstrap diode uh, of this forward voltage drop with forward current. Similar to that, we have another one which is going to be forward voltage drop and IF. This is the zoomed version you can see. So zoomed version, it is showing you up to 3.5 volt maximum, which is reaching up to 25 milliamperes of current. Let us talk about temperature of LVIC versus over voltage or like output characteristic, which is going to be high temperature. Okay, so VOT will be what based on the temperature. So as my temperature is increasing, my VOT is also increasing, you can see. So at 95 degrees centigrade, my over voltage protection pin will be showing you 2.76 volt. That's the understanding that we should have. And these three curves are basically like for typical, minimum and maximum. So maximum it can show you 3.03 volt, and minimum it can show you 2.76 volt. So if we have the understanding of all these characteristics properly, it is very easy to design this particular IPM circuit. Let us talk about pattern wiring around the analog voltage output circuits. Okay, so what happens is, this is our terminal. Okay, and let us say this is my terminal, which is VOT, and VOT is going to have internally, you can see we have temperature signal, going to have proper amplification and buffering, and we have protection as well. So you can see there is a up and down ESD diodes are available. Coming back to the output side, so once we go to connect it to my microcontroller signal, we can pull it down with 5.1 kilo ohm with a proper ESD diode and send it to my MCU. Okay, so that will be monitoring the output voltage uh, at the temperature pin, right? So it can be sent to my ADC of microcontroller or whatever it is. If you want to read in very detailed manner, you can read out all these details, these notes. This will be very useful. If we talk about mechanical characteristics, so it has given you what is that mounting torque, like this much torque you should apply while screwing it into the board, and we have lot of like terminal pulling strength and terminal bending strength, so that much can be like taken into account. That's all about while mounting or while assembling this particular IC on the PCB. Okay, let's talk about recommended temperature or recommended operating conditions. So this is the thing that I wanted to tell you. The VCC supply, that will be the supply which will be like given the high voltage DC, that will be typically 300 volt. So we'll try to like give around 300 volt, and maximum it should go to 400 volt, otherwise it will be a problem. If you talk about control voltage supply, as I was telling you, so generally we give 15 volts. That's the reason it is shown here. It is shown here also 15 volt. We just vary from, let's say, minimum 13.5 to maximum 16.5. That is 1.5 volt up or down can happen, but 15 volt is nominal voltage. We have control supply voltage of VDB signal also for like like you can see U phase, V phase and W phase. So that is also 15 volt, and this can be always protected using some Zener diode, so that it will be always like a good design that will show you during our circuit design example. And we have like a total time date, like we have to blocking time, or you can say like PWM dead time. So PWM dead time will be minimum 1 microsecond. If you talk about PWM frequency, so that can be maximum 20 kilohertz. So we will generally work with like 5 kilohertz or 10 kilohertz. That's more than enough for any of the motor driver designs. That's all. With this, we can proceed to next one. We can see one more thing at last, like junction temperature must not exceed 125 degrees centigrade and minimum minus 20 degrees centigrade. So we make sure the IC is working between these two temperature, which is minus 20 degrees centigrade to 125 degrees centigrade. And the PWM on time and off time minimum pulse width is like 0.7 microsecond, otherwise there will be a problem. So you can see for PWM 5 kilohertz and PWM 15 kilohertz, it has been tested for allowable RMS current as well. Good. Now talking about timing chart for deep IPM protective function. So we have this timing chart. So that will be actually coming during our like a design phase. So just we'll skip right now for this, and then we have coming down. Yes, this is the example circuit that is shown here. So this example circuit will actually give you an understanding of. So let me take this particular circuit properly. So we have a microcontroller part, and that is what is going to get connected to our like 6 PWM, which is higher side PWM. This one, these three, UP, VP, WP, and this is UN, VN, WN, that is lower side PWM. So these are the complementary PWM, 6 PWM that we will be supplying. So there are a lot of like functionality that we will be giving, let's say like RC filter, or maybe isolation, or maybe like translator or buffers, or all those things we will be trying to put here for our better circuit functionalities. So this is what it is telling you, like in case of being affected by noise, it is recommended to insert one RC filter. Okay, coming back to our voltage control supply. So you can see the voltage control supply with UFB to UFS. UFS is actually ground, so that way you can understand, but it can be always supplied with one capacitor along with one filter capacitor of 0.1 microfarad you can take up, and it has to be protected with a Zener diode. So all the three like U phase, V phase, W phase control voltage supply can be given through the capacitors. Okay, coming back to the next part, which is going to be VP. So VP is going to be like getting a voltage of 15 volt, that will is my current voltage supply, that will be my VP1 or VN1 that you can see for high side and low side control supply. Okay, it is also protected with Zener diode that you can see. Coming back to my output for fault protection. So fault output is there, which is going to be pulled up. This is because of open drain kind. So this has been pulled up, and it is going to indicate to one of the GPI of microcontroller. So whether it is high or low, based on that it can take a decision whether my IC is in fault condition or it is in normal operation. Coming back to the temperature output pin. So temperature output pin is pulled down with 5.1K, and it can be sent to my analog voltage signal, so ADC, and this ADC will be monitoring what is the temperature of this particular IC based on this particular VOT pin. It is actually connected inside with some thermistor like NTC thermistor, and that's how it is working. Let's move to the secondary side or right side. So as you can see, motor is connected to my U, V and W phase, and this is the power supply pin that will be there, P, which is taking the high voltage, which will be taking up around 300 volt with a DC link capacitor plus one filter capacitor. If you want, you can put it for better design. Back to the current monitoring of each of the lines of U, V and W phases, we will be connecting a shunt resistor, and this shunt resistor can get into the scene pin for comparator functionalities, and it can also be like going to the let's say amplification and sending it to monitoring for ADC pins. So this was all about this particular circuit. We will be seeing much more detailed application circuit with a particular application or actual project that we have already designed for lot of motor driver application. Let us say like ODU unit, like air conditioner, as well as dishwashers. We have refrigerators, and then we have motor drivers for water pumps. So all those things we have already designed. We'll give you 2-3 examples of actual circuit with each and every values mentioned in the circuit, so that it can make you understand how to design your circuit for a particular application, and at the same time you will be mastering the circuit design analysis or techniques or guidelines for your any application that you have in your mind or in your projects that is there in your industries. So that's the main cause or main focus or main vision for this particular session, to make you understand how to read the data sheet and how to understand each and every pin functionalities, and what are the things that is taken care while designing a circuit using intelligent power modules. And as I already mentioned, the Mitsubishi Electric is the pioneer of IPM, and they are the first one who has put all these my my gate driver circuit as well as controller circuits and all, and with IGBTs all in one package, and coming up with a proper packaging like pin differences or something like that, so that you can avoid all hitting or all those things, right? So Moving to the next part, so for this particular circuit design, you can read out this particular 12 guidelines. So these 12 guidelines will make sure you to understand what are the things that we need to take care while designing the circuit. Anyway, through our design and our explanation with the circuits, you will be able to understand each and every point one by one, but there is no need to waste time here right now to read out each and every points. Let's talk about some of the guidelines that is given in the datasheet itself. So as you can see, my microcontroller IO interface circuit. So whenever there is a IO that is getting connected, let's say we have PWM signal that has to be like coming from the microcontroller. So as you can see, they will be accompanied with RC circuit or RC filter. So you can see all these high side PWM and low side PWM must be taking RC filter that is recommended. Coming back to the fault output pin, so fault output pin must be pulled up, and as well as it can be accompanied with one RC filter that then it can go to my microcontroller GPIO. Okay. Coming back to pattern wiring around the shunt resistor. So shunt resistor, you can see we have like NU, NV, NW, and they all can be connected to a single shunt resistor for single utilization. Then that can go directly like this, and then it can get connected to my VNC pin, or CIN pin was also there, that we'll see. With each of the three lines has to be monitored separately. Then we can connect a 3 shunt resistor like this, and then it can go to the VNC pin. Okay, so this is how we have to wire around the shunt resistor. Coming back to external short circuit protection circuit using 3 shunt resistors. So as you can see, we have we have NV and NU, NV, NW. So those are connected to 3 shunt resistor, and they are going to get connected to my VNC pin, right? Now coming back to what is the current rating that is going into each one of them. So what happens is this, basically they can be taken into account through an RC filter, and then there will be a comparator. So this is nothing but some references there, and what is the voltage seen at this point, that will be compared, and this is how it is going to go into output to our CIN. So CIN is the pin which is going to have a comparator which will tell you what is the highest current rating that is flowing through each of the lines. Otherwise it will shut it down accordingly. Good. So these are the package outline. You can see what is the length and width of the package. We have around 32 mm length, and around this is around how much, like 18.9 mm or 18.8 mm width. So this is the complete package diagram, and about some other parts. So that's all. This about this particular data sheet explanation, and how we have understood this SLIMDIP IPM from Mitsubishi Electric with all these functionalities and details that we have seen here. So basically what is our next step is take this SLIMDIP-S IPM, and then we will design one circuit which will be called as implementation. So in implementation phase, we will be designing complete circuit with all the values and parameters with a particular project details. So thank you so much.